Hello guys, today we're going to design microstrip patch antenna using CST software. So here is the complete design. At the front, we have the patch. It's connected with the feed line. And then at the second layer, we have the substrate. And at the back, we have the fully ground layer. If you look at the bottom, we have the waveguard port. So basically, before we design our antenna, we need to know at which frequency we want to design our antenna. First. Second, we need to know what is the material that we are going to use to design our antenna. For example, if we want to design FR4, we need to know what is the dielectric constant of the FR4 and what is the thickness of the FR4. So from that value, from that parameter value, we can calculate to find the width of the patch and the length of the patch. So let's take a look. For example, if we want to design antenna by using FR4, so at the top and the bottom layer is a copper layer, and in the middle is an FR4 made from the glass fiber. So if you look at the design of the microstrip patch antenna, we have the patch antenna rectangular at the top, and it's connected with the feed line. So we need to find out what is the length and the width of our patch antenna. And next, we have the substrate layer. So in our case, we're going to use FR4. So we need to know what is the height or the thickness of the FR4 and then the dielectric constant epsilon R of the FR4. And then at the top, we have the ground plane, the full layer of the copper. So if we take a look layer by layer, at the first layer, we have the patch and feed line. The material is made of the copper and is conductive. So the conductivity value for the copper is 5.810 power of 7 Simon per meter. And the thickness of the copper is 0.035 millimeter. And the second layer, we have the substrate layer, which is material of FR4. The dielectric constant epsilon R is 4.3 and the thickness is 1.6 millimeter. So the spec of the FR4 parameter value you can get from the data sheet they available on the market. So the value of the constant basically depend on the which material that you use. If you use the Rogers, the constant might be not 4.3 and the thickness might be different as well. And then third, we have the ground layer, which is made of the copper, same as the patch and feed line, and they have the same value of the conductivity and the thickness. Next, let's say we're going to design our antenna at 2.5 GHz. So now we can use this formula to find the width of the patch. So basically this formula we can get from the book Antenna Theory, Analysis and Design. So if you look at the chapter of the microstrip patch antenna, here you have the explanation of the microstrip patch antenna. At the top it says patch, and then the second layer is the substrate, and then at the bottom it has ground plane. And he have the different type of geometry. So for now we're going to focus on the rectangular patch antenna first. And here is the effective dielectric constant, one of the family that we are going to use. So here is the width. So we're going to use this formula to find the width of the patch. And then this formula to find the length of the patch. Okay. So to find the width is equal to the c, which is speed of light, equal to 3.010 power of 8 divided by 2f. F is our desired frequency, which is 2.5 gigahertz. So you need to put the value 2.5 G, 2.5 gig inside the formula. And then you need to know the dielectric constant epsilon r of the substrate. In our case, we use FR4. So the value is 4.3. So now you can get the width of the antenna. So next, you need to find the length. You need to know the formula is C divided by 2F effective dielectric constant minus 2 delta L. So before you calculate the L, you need to find out the dielectric constant by using the effective dielectric constant by using this formula. So you know the substrate of the dielectric constant previously 4.3, and then the H, which is the height or the thickness of the substrate, 1.6 millimeter, which is you need to put on the formula 1.6 m inside the formula divided by the width, which is you find for the previous calculation. And then next you need to find out the delta L by using this formula. So you know the effective dielectric constant from the previous calculation, and the width from previous calculation, and height is the thickness of the substrate. So when you get both value, you can apply on this formula to find the length of the patch. So guys, if you notice, the length and the frequency, also for the width and the frequency, is a non-linear. So it means that when we design the antenna at the higher frequency, when the frequency is increased, the width will become smaller, or the width will decrease. So if you have to design at the lower frequency, the width will become bigger because it's a non-linear to each other. Okay, let's say if you have calculate all this value parameter, and you want to check is it your calculation is correct or not, you can double check by using the website. So we type Microstrip patch antenna calculator. For easy, we go to the image and find this image and visit the page. So from here, it will automatically calculate for you, but you need to know the value of dielectric constant. So for our case, we're using FR4, it's a 4.3, and the dielectric height, which is the thickness of the FR4, is 1.6. The frequency that we want to design our antenna at 2.5 gigahertz. So click synthesize. So you got the value of the patch. The length is 28.56 here. The width is 36.585 millimeter. Next, you need to find what is the length and the width of the feed line. So you can go to you can type feed line antenna calculator, go to the image and find this feed line image, click. So from here, if we automatically calculate the feed line, so you need to input the dielectric constant 4.3. So you need to insert the 1.6 for the height or the thickness of the FR4, the frequency at 2.5 gigahertz, and the Z0, the impedance of our feed line antenna. Basically, we using 50 ohm, which is the same impedance as the SMA connector available in the market. It also have the 17 ohms in the market, but for now we focus on 50 ohms. And the dielectric length we're going to use is 90 degree. Click on synthesize. So you will get the value or the width or the feed line 3.11 millimeter, and the length is 60.59 millimeter. So once you get both feed line and microstrip pH value, so you can start to design your antenna. For example, here we have our pH size for the calculation before, and the feed line. So the second layer and the third layer is a substrate and ground layer. It will be bigger than pH. So let's say we add more 20 millimeter for the pH size. So it becomes 56.86 millimeter, which means we have the gap here is 10 millimeter at the right, and at the left is 10 millimeter gap. It's bigger than the pH. And from the pH here to the top of the substrate, we add another 10 millimeter. So 10 plus with the pH length plus with the length of the feed, so we get 55.16 millimeter. So let's try design. Or if you are first time open the CST, you will need to create new template. For my case, I already opened the CST software, so I go to this white page to create a new project. For your case, you create the new template, choose the microwave, choose the antennas, click next, and choose the planar pH. Click next. We're going to simulate our antenna in time domain, so click next. So here the default unit that we're going to use, the dimension we're going to be used is millimeter, the frequency in gigahertz, so click next. And then this is the minimum and maximum frequency that we want our CST to simulate the antenna, our antenna. So let's say our center frequency that we're going to design is at 2.5. So we need to put the value of the frequency minimum below than 2.5. Let's say 1.5 is the minimum, and the center is 2.5, and the maximum will be 3.5 gigahertz. So we want to make sure that our operating frequency at the middle. So our middle is 2.5. So it's balanced. From 1.5 to 2.5, the gap is at 1 gig, and from 2.5 up to 3.5, the gap is 1 gig as well. So next we can set the monitor of the E field, H field, or far field here, or we can set later. So let's say I want to set the E field first. So click, and then the frequency we want to set at our operating frequency 2.5 gigahertz. So click next and finish. So here, don't forget to save your project. Click on save here, namely the project. So here we have the box where the X, Y, Z exists. And then if you don't want the background here, so for me, I prefer to hide. So go to the view, and I want to hide the working plane, so have a better view. So if you want to see from the front, you can press 5 on your keyboard. So it is a front view. Y axis is our length of the antenna. X axis will be the width. Z axis facing you, it will be the thickness of our antenna. So we want to design the antenna from the bottom layer. It will be easy. So we click the modeling, create the box or brick here, and press ESC on your keyboard. So here we're going to name the third layer will be ground. So there are two methods to create. First, you can put the value, or you can give the name, and and insert the value later. So here I show you, we're going to put the value first. So X min ground layer will be the width. The width of the ground layer is same as the width of the substrate layer. So it's 56.86. So we're going to design at the middle, at the center, coordinate 0. So we're going to divide by 2. Since this is the X min, so we put the negative, and X max will in positive, 56.86, divided by 2 as well. So it will be designed the half on the right side, which is positive side, and then the other half it will design on the left side, which is in the X min side. So next is the height y axis. It will be the length of our ground layer. So we start from the 0 and then up to X max, which is our height of the substrate, and the ground layer is the same height. So we use 55.16. So next is Z min is referred to the thickness of our ground layer. So we start from 0 and then the ground layer of the copper layer, the thickness of the copper layer, you can see the copper of the thickness of the copper layer is 0.035 millimeter. And then the material that we're going to use is copper. Load, we can look from the material library, and then we scroll down and find the copper. So we're going to use the copper, and here you can see the dielectric constant is 5.8 10 power of 7 Simon per meter, and click on load, click preview. So it will create the ground layer here. Click OK. So let's say if you want to make the edit on the size of the ground layer, so go to the component, click the plus sign here, and go to the component 1, and double click on the ground layer. So go to define brick, double click. So here you can edit from here the size. Okay, then another method, you can put the name here. For example, this is the X min for ground, so I will name it as the XG underscore min, XG underscore max. So easy for me to remember. And this is YG underscore min, YG underscore max. Z min is start from 0, and then Z max, the thickness, I name it as a T thickness, G ground, and then I click preview. It will be ask you the value of the XG min is same as previously. We're going to use 56.86. So it is the mean, so we need to put minus, and we divide by 2. So next is the SG max, so it will be positive. The size is here, divide by 2. And then YG min, we start from the 0. YG max will be the length of substrate and ground, which is 55.16. The thickness of the ground layer will be 0.035. Click OK. So you can close. So all the parameter will be appear here. You can see TG, our thickness. So if you want to edit, you just double click here. So you can just edit from here. You need to go to the component ground layer here. So in your case, your parameter list may be at the bottom. For my case, I prefer to put at the right side. The next, we're going to design the substrate layer. Go to the brick, and then press escape. We're going to name it as a second layer, which is substrate. And then xmin, the xmin, since the layer of the ground and the substrate is the same, so we're going to use the previous parameter. So here I'm going to use the xg underscore min, since it's at the same size of the ground. The y will be yg min yg max. For the thickness of the substrate will be designed on the top of the ground layer. So we start from the Tg, which is the thickness of the ground, and the Z max Tg, we're going to plus the substrate of the thickness of the substrate, which is Ts, namely as a Ts. And then you can click on preview. So it will ask the thickness of the FR4 will be 1.6. Click OK, and then the material will be FR4. So load from the library. So we're going to use FR4 low C, where the epsilon dielectric constant is 4.3. And click OK. So substrate is now created on the top of the ground layer. Okay, you can press 5 and space to see the front view. So now next we're going to design the feed line here. The width is 3.11. So click on the brick, escape, namely as a feed line. So xmin, I'm going to name it as a sf, which is the feed, minus min sf max yf min yf max. We're going to create on the top of the substrate. So at the below, here I have the thickness of the ground, Tg, and plus thickness of the substrate, Ts. For Z max, we're going to plus the thickness copper layer of the feed line. So namely as a Tf. So click preview, you will ask the width of the xmin here, 3.11. So we're going to design at the middle as well. So we put negative 3.11 and we divide by 2. And the xmax will be 3.11 positive divided by 2. Yf min, we start, the bottom here is a 0. Up to, we're going to see the height or the length of the feed is 60.6. Tf, the thickness of the copper layer, will be 0.035. So here, click OK. You can see the material should be copper layer, which should be yellow, but now feed line is a FR4. So what we can do is go to the feed line, right click, go to the assign material. So from here you can change the material. It should be copper layer. So click on copper, click OK. So now you have the copper layer or the feed line. So next we're going to design the patch here. So go to the brick, escape first layer, namely as a patch. So as min, I'm going to name it as a XP, so it's a patch underscore min. XP underscore max, YP underscore min. And from here, if you notice, we're going to design our patch at the top of the feed line. The top of the feed line is the YF max. So we can use the YF max here. YF max. So we're going to start design from here, right? So for X max, starting from YF underscore max, so we can namely as a YP underscore max here. And then for thickness, it's the same thickness at the feed line. We start from TG plus TS, and then we need to plus the thickness of the copper layer. Since it has the same thickness at the feed line, so we're going to use TF. And then the material will be copper. Preview, we will ask the width of our patch. Here, the width of the patch is 36.86. Since it's the minimum, so we're going to put minus, divide by 2, positive 36.86 divided by 2, and it will ask you the maximum of our patch here, the maximum value here, the YP max here. So the value here is 28.56 plus 60.6. So it will be 45.16. Okay. Click OK. So now you have the patch on the top of feed. Okay, so next we're going to create waveguard port. So what you can do is you can hold the control on keyboard and click the mouse and you can rotate, or you can go to the view, click rotate here, and you can rotate your antenna. And we need to zoom the feed line here. We're going to create the mark here. So go to the modeling and you click on pick point edge S here. You can press S on the keyboard or you can click here. So we're going to choose the bottom of the feed line here. Make sure you not click on the line or the top of the line here. Not, we're going to choose the middle of the feed line at the bottom here. So double click. So it will mark here. You can see our feed line. So we mark the bottom of the feed line here. So go to the home, choose macros, go to the solver, go to the ports, go to the calculate port extension coefficient. So it will be automatically put the value of the width of the feed line, the thickness of the substrate FR4, the dielectric constant epsilon R of the FR4. So we click calculate. So it will give the coefficient value or the K here, the the size of the waveguide port. So you just click the construct, it will be automatically create. So close. So here is our port. If you want to see the dimension of the port, you can go to the port here and double click here. So this is the automatically dimension that CST create for the waveguide port. So next, you're going to simulate, go to the setup. So the accuracy, if you choose more 50, minus 50, minus 50, it will be more accurate, but it will take more time to simulate. So for this case, I prefer minus 30, it will be enough. And click start. And you can see the progress here, click on progress. Scroll down. So you can fast forward, it will take time to finish the simulation. Okay, let's see the result. Go to the 1D result. Go to the S parameter, which is S11 or reflection coefficient. If you can see the result is just a little bit minus 10 dB. We want our result to be below than 10 dB, and the frequency should be on 2.5. So what you can do here, if you want to see, you can put the marker here. You can press M and go to the line and double click. So you can see it simulate the center frequency now is 2.5. We want 2.4. We want 2.5, and then it's just a little bit below 10 dB. So we want more deep to have the better impedance. So what you can see, what you can do is go to the 2D and 2D result to see the impedance. It should be 50 ohm. Go to the port modes, go to the port 1, go to the E1. You can see the line impedance is 47. So we prefer 50 ohm. So we can do some edit on the feed line. And we want the frequency is 2.5. So click on the components. So the feed line, we adjust at 2 point, we decrease 2.9. Click enter. So here you can read the current result or you can store. And the Fmin as well, you need to be in balance. Also need to be 2.9. So next you can update, you can press F7. On some laptop you need to press Fn and F7 to update. So here you update the current parameter of feed line 2.9. So next what we can do is, since we notice that we already delete result, so if you notice that the previously our simulation at 2.4 gigahertz, but we want at 2.5 gigahertz, so you can edit the width of our cache. Because if you see here, our frequency, we got 2.4 here, and then the width we use at speed is 36.86. 36.86, the frequency is 2.4. So if you want frequency 2.5, the higher frequency, so we need the smaller width. So we need to decrease the size of the width. So let's say we decrease the size of the width here, 36.5. And to have the better impedance matching, we can create the slot here at the right and the left side. So let's create. So you can press S and then pick the point here, double click, and create the brick box for slot. I'm gonna name it as a slot get. So for X min, we name it as a XSG slot get underscore min, XSG underscore max, YSG underscore min, sorry, YSG underscore max. Thickness will be the same thickness as a patch, which is we start from the thickness ground plus T as substrate. So X mat Tg plus Ts for substrate, and then plus the thickness of the patch, same as the thickness of the feed, Tf. So we're gonna preview. So YSG min will be here, and then here will be XSG max. So our XSG max, the coordinate x will be minus 1.45. Let's say we want the gap of the 3 millimeter, so we plus 3. So minus 1.45 we plus 3 will be minus 4.45 for SG min here. So here have a 3 millimeter gap. Click OK, and then XSG max is here. So the coordinate here is minus 1.45. And the YSG min, the minimum here, the Y axis is here. So if you can see X, Y, Z, so here is X, Y, Z here. So Y is 60.6. Click OK. And then we want to create up to here around 5 millimeter. So 60.6 plus 5 will be 21.6. So click OK. And then we want to create another slot at the right side. So what you can do is you can use the transform, and you can use the coordinate by pick the point. So first we need to clear this point, press D, and then pick the point, press S, one point here, double click, and then we want to create another point, press S, then double click on point here. So now we have 2 points. So we want to create another slot here by duplicate. So click slot get, click transform. So it will transform to another side, which is here on the right side. And we want to maintain this slot, so we click copy, so it will duplicate. Click OK. So now we have a 2 slot. So to remove this side, to create a gap, so click on patch, click on boolean, click on substrate, and click on slot gap and press enter. So we create the slot. So do the same thing for the right side. Click on the patch, go to the boolean, click on substrate, click on slot gap 1. So press enter. So you have the 2 slot here. And if you notice, if you want to combine the feed and patch, what you can do is press on patch and click on boolean, click on add, and you click on feed line, and then press enter. So you have the connected feed line and the patch. Actually, it doesn't matter if you're not connected, it still will produce the same result. So here our complete design. So let's say if you want CST to simulate not just at the one parameter. This one they have a 3 millimeter gap. So if we don't know what if the final result will be, so we want the CST to simulate at the multiple different gap. So we can do is go to the home, go to the parameter swap, create new sequence 1. So create new parameter. So here we're going to change the the, the parameter that we're going to simulate will be SSG mean. So we choose SSG mean. So let's say if we simulate from 4.45 up to 7, let's say 7.45, and then how many sample you want? Let's say we want up to 5 sample. So it will be simulate 5 times for different gap of our slot. So click OK. So here you can check first. Click check. So you can see the gap. It will be increased. So that's what we want the CST to simulate. So you can check the view log file. So the CST will simulate at SG mean minus 4.45, 5.2, 5.97, sorry, 5.97 and 6.7 and at 7.45. So click OK and click start. So you can fast forward, you will simulate 5 times. Okay, let's see the result. Go to the S parameter. So if we see, this is the final result, the last parameter result, where SSG is at minus 7.45. But previously, we simulate at 5 different parameter, right? So what you can do is go to the S11 here. So it will show you all the 5 different results. So you go to the first one is a SSG mean as minus 4.45, double click. So it's not reached at 2.4, 2.5. So we're going to find which is the best result. Here is at minimum SSG minimum at 5.2. Here is at 5.97. Here is 6.7. So here is our result that we want at 2.5. And if you see at the last parameter is 7.5. So it shifted a little bit more than 2.55. So if you go to the FAFI result here, FAFI result, relax gain. Here actually this FAFI result is belong to the last parameter simulated. This is at 7.45. But we want our result at 6.7. So what you can do is right click and choose set parameter to run ID. So we want the CST to run at ID 4 where the SSG max is 6.7. So click OK. And click on component here. So you need to update. Press F7. So SSG will be minus 6.7 and you can start simulate. You can fast forward this video. Okay, let's see the result. S parameter here. Our S11. So we want below minus 10 dB and frequency at 2.5. So you can put the marker, press N, double click. So at 2.5 gigahertz, so S11 is minus 35.4. And then we want to see the bandwidth. So you can press M to put the marker here, double click, and then and then the marker here, double click, and then after you done put the marker, you press escape. So we want to make sure it's at minus 10 dB at least. So here marker 3 minus marker 2 to get the bandwidth. So bandwidth at 2.54 minus 2.45. So you will get the bandwidth here. Next we look at the far field result to see the directivity value and the realized gain. So the realized gain here is 2.5. So to check the directivity, you can go here, click the directivity. So the directivity here is 6.3. So you also can show the structure of the antenna by click here, and you want to transparent the far field. So we can see here from here. So it's mostly it have a directional antenna. So the radiation at the front, the main loop, and then we have the slightly back loop here. So if you want to see more clear, you can click on linear scaling. So you can see this antenna is directional antenna. So the radiation goes to the front. Alright, next you can see the 1D result. Click here. You can see here actually is your antenna. So mostly you have the main loop at the front, and you have the minor loop at the back. So what you can do is you also can cut the angle of the phi at 0. You can see. So here you can see this is the waveguide port. So we looking from the waveguide port, and here is your antenna, and you can see the loop, main loop at the front of the antenna. Next, what you can see is you can see the surface current of the antenna. Go to 2D, 3D result, surface current. So here you can click on animate field to see how the current flow on your antenna. So it's going from the bottom feed line, go through to the mesh, and go back, go up, down, up and down. So you want to see more clear, you can go to the properties, plot properties, and you can adjust the scaling size. So you can see more data right here. So close. So you can see here is the guideline of the line of the color. So the green and yellow will be the highest of the current, mostly at the patch, right at the center of the patch. Here is amount of the current is more higher compared at the edge of the patch here. So you also can see the different current flow from the different view. For example, here you can see, and we can see the current flow going from the top to the up. So for the greater view, we look at from for the arrow here. So that's all for now, guys. So next time we will look at how to design antenna for new material that they don't have in the library. So that's all. Thank you. See you soon.